So, the Chapter 7 homework we do on Monday the 8th. The Chapter 7 quiz will be on Monday the 8th in SI. Today and the 10th are makeup lab dates. If you need to, you can come in on the 8th as well. But I think most of you have all your labs done. On Monday the 8th, we'll be doing a review of chapters 5, 6, and 7 in lecture. And the exam the last exam on chapters 5, 6, and 7 will be on Wednesday next week, the 10th. Any questions about that? So today we will be covering, as voted on last time, chapter 10, which will not be on the test. So this is just, there was time, we'll talk about what you guys voted to look at. So this is chapter 10 on nuclear physics. So we're going to talk about the atomic nucleus. So the characteristics of the atomic nucleus are important to our modern society. We'll talk about how we can use things from that for diagnosis and treatment of cancer and other diseases, geological and archaeological data, chemical analysis, nuclear energy and nuclear disposal, the formation of new elements, how solar energy is generated, and the generation of electricity. So the earliest thoughts about the elements probably started with the Greek philosophers from around 600 to 200 BCE. They were the first people to speculate about the basic substances of matter. There were a few different ways to do this. There were other speculations, but the Greeks were the first to talk about it as elements. There were, some basic building blocks that things were made of. Aristotle speculated that all matter on Earth was composed of only 4 elements: earth, air, fire, and water. And then later a 5th one was added to represent the stuff in the heavens, like quintessence. He was wrong on all counts. We've now defined elements as the most basic sort of atom, things that can't be changed by chemistry. And we have symbols for elements. The Swedish chemist John Jacobs Berzelius in the early 1800s used 1 or 2 letters of the Latin name of various elements to designate each element. This is why certain elements have weird symbols to English speakers. So copper is Cu because the Latin name is cuprum. Gold is Au because the Latin name is aurum. Iron is Fe because the Latin name is ferrum. Lead is Pb because the Latin name is plumbum. Mercury is Hg because the Latin name is hydrogarum. Potassium is K because the Latin name is kalium. And, if you look at the periodic table on the wall back there, you can see we have significantly more than 4 elements. I believe it's like 112 that we've gotten to. There's 92-ish naturally occurring ones. But we've made artificial elements up to, I think, 112. So since Berzelius's time, most elements have been symbolized by the first 1 or 2 letters of the English name. You're not expected to know any of these, but this is a table of common elements. So these are some common elements. So things like aluminum. Now, all matter is composed of atoms. An atom is the sort of basic building block of matter, but atoms have parts. In chemistry, when you're doing chemistry, atoms don't change, but atoms are made up of parts. In fact, part of it does because atoms have electrons that orbit them, and the electrons are exchanged in chemistry. So an atom is composed of 3 subatomic particles: electrons, which are negatively charged, protons, which are positively charged, and neutrons, which are neutral. And the nucleus of the atom contains the protons and the neutrons. They're also called nucleons, while the electrons surround or orbit the nucleus. And electrons and protons have equal but opposite charges, which is why the electrons are attracted to the nucleus and orbit the nucleus. Chemistry involves the electrons of atoms interacting with each other. That is what is happening with chemistry. All chemical bonds are electrons interacting with each other. Chemical reactions are electrons moving around. So the major constituents, the electrons are tiny compared to the nucleons. So they have a charge of negative 1.6 times 10 to the minus 19. You just call it E, minus E. Their electronic charge is minus 1. Their mass is 9 times 10 to the minus 31. Protons have a mass of a charge of plus E, or plus 1.6 times 10 to the minus 19 coulombs. So they have an electronic charge of plus 1. Their mass is 1.63 times 10 to the minus 27. So these are about 2,000 times the mass of electrons. And neutrons are 1.675 times 10 to the minus 27. They're a little bit heavier than protons. They're neutral, they don't have a charge. Protons and neutrons make up the nucleus of the atom. The number of protons is what determines what element an atom is. The protons and neutrons have nearly the same mass and are about 2,000 times more massive than the electron. The electron was discovered in 1897 by J.J. Thomson. The proton was discovered by Rutherford in 1918. And the neutron was discovered by James Chadwick in 1932. So J.J. Thomson's original plum pudding model was that if you had the electron, the idea was that electrons were sort of distributed throughout the atom through some sort of continuous positively charged substance. So it predicted that alpha particles would pass through the evenly distributed positive charges of the gold atoms. But some of them bounced off. So the thought was that it was like shooting a bullet at tissue paper and it bouncing. Because what actually happened was that some of them bounced off of nucleuses, the alpha particles. Most of them passed through, missed the nucleus, but some of them deflected off of the various nuclei. This was not at all what was expected. Alpha particles are actually helium nuclei, but they didn't know that at the time. And only about 1 out of 20,000 alpha particles bounced back. And Rutherford could only explain this by assuming each gold atom, had a positive charge concentrated in a very small nucleus. And the diameter of the nucleus is about 10 to the minus 14 meters, while the orbit of an electron is around 10 to the minus 10 meters. So the nucleus is about 10,000, about 1/10,000th the size of the atom in question. And 99.97% of the mass of an atom is concentrated in the nucleus. So the volume or size of an atom is determined by the orbiting electrons. So the diameter of an atom is about 10,000 times the diameter of the nucleus. And if only nuclear material, protons and electrons could be closely packed into a sphere the size of a ping pong ball, it would weigh 2.5 billion tons. Now, things made of macro scale size nuclear matter exist. They're called neutron stars. They are insane, but you only get them after the death of very large stars. So this is a nucleus. It's tightly packed protons and neutrons, because a neutron star packs the mass larger than the sun into something the size of a city. It's 7.2 times 10 to the minus 15 meters across. and it's a ball of protons and neutrons. Protons are positively charged, neutrons are neutral. You would expect this to blow itself apart because positive charges repel each other, but it doesn't. So what's holding it together? There is a force called the strong nuclear force that is holding it together. And that's why we have both protons. That's why you need neutrons as well as protons, because neutrons don't contribute to the outward pushing, but they do help with the inward pulling of the strong nuclear force. So the atomic number is the number of protons in the nucleus. It defines the element. It's always the same for any given element. And it also designates the number of electrons the atom would normally have. If an element either gains or loses electrons, the resulting particle is called an ion. So you may have heard about various ionic things or ionized things. That just means gaining or losing electrons. So for example, if a sodium atom loses an electron, it becomes a sodium ion. If a chlorine atom gains an electron, it becomes a chlorine ion. Then they're attracted to each other, and that's how you get salt. But when we describe something specifically, we write the chemical symbol. We can write the atomic number down here, but we can also write the chemical symbol and the atomic number tell us the same thing. And then up here we have the mass number, which is the total number of protons and neutrons. It's the total mass, roughly, of the nucleus. So isotopes are when the number of neutrons vary in the nucleus of a given element. Given element always has the same number of protons, but it can have different numbers of neutrons. And they vary, and some isotopes are more stable than others. So for example, if we look at one of the simplest, well, we look at the simplest of atoms, hydrogen. Hydrogen has 3 isotopes that occur. You could just have a proton, that's normal hydrogen, that's everyday hydrogen. You could have a proton and a neutron. That would be written as 2 hydrogen. It's also called deuterium. Or you could have 3 hydrogen. So this is a proton and a neutron. And this is a proton and 2 neutrons. That is tritium. So only about 100, okay, we've gotten up to 118. Only about 118 chemical elements are known, but the total number of isotopes is about 3,000. So we might have got enough. I don't even know what the highest is. We've hit a sort of a practical limit on element synthesis, and all the big ones last for a fraction of a second anyways, so. The total number of isotopes is about 3,000. Because there's a lot of things where you can have one or more. Like, you know, when I did my research, I was looking at what happened when you change the amount of helium-3 in solid helium. Because helium-3 is a lighter isotope of helium. Normal helium is helium-4. So some isotopes have, some elements have several isotopes, like carbon-12, carbon-13, and carbon-14. So the carbon in your body is mostly carbon-12. It has a bit of carbon-13 and a bit of carbon-14 in it. So isotopes of a single element have the same chemical properties. They don't vary chemically much. For the very light ones, they can, because the change in mass can be significant enough to have some chemical effects, but generally they don't. So like there's some non-trivial chemical effects going from hydrogen to deuterium because you're doubling the mass. But it's not very, but the effects are still pretty small even then, because they have the same electrons on the outside. But they have different masses due to varying number of neutrons. And due to the various masses, isotopes can behave slightly differently during reactions. And they can be identified by various techniques like NMR and such, or you can isolate them. You can actually use unstable isotopes for dating. So here's hydrogen. The three naturally occurring isotopes of hydrogen are protium, hydrogen 1, it's just a proton. Deuterium, 2 hydrogen, which has a proton and a neutron. It has a mass of 2. And tritium, you can call that hydrogen 3, which has a proton and 2 neutrons. Tritium is unstable. This is radioactive and will eventually decay. I don't remember how it decays. But about 1 atom in every 6,000 is deuterium. Deuterium is stable. And about 1 in 10 million is tritium. And you can have something called heavy water, which is water with deuterium in it instead of hydrogen. And that happens to be useful for certain sorts of measurements, like NMR measurements, because in NMR, deuterium has a different frequency than hydrogen. So if you make your solvent out of heavy water, the water signal vanishes from your measurement. And then you can also actually use the deuterium for things, which is why we have a bottle of heavy water in the lab next door. Not that hard to get. But so you could just filter it out of regular water, it turns out. Because again, about 1 atom in every 6,000 is deuterium. And if we want to determine the composition of an atom, we can determine the number of protons, electrons, and neutrons in, say, a fluorine 19 atom. The atomic number is 9, so there are 9 protons and 9 electrons. The mass number is 19. So that's the total of protons and neutrons. So 19 minus 9 means there are 10 neutrons. And for most of these smaller elements, the number of protons and neutrons will be about the same. Though when you get to heavier stuff, you end up starting to have more neutrons. Because it turns out you need more neutrons to keep things stable. So protons and neutrons are in the nucleus. Electrons orbit around the nucleus. The mass number is the number of protons plus neutrons. The atomic number is the number of protons. The neutron number is the number of neutrons. An isotope is an element with a different number of neutrons and the same number of protons. So the atomic mass you see on a periodic table is a weighted average of the mass of an element in a naturally occurring sample. So if you look at the atomic mass of hydrogen, for example, you'll see it's a little bit more than 1. That's because the deuterium is causing it to go up a little. A carbon-12 atom is used as the standard and is assigned the atomic mass of exactly 12U. And the weighted average mass of all carbon is slightly higher than 12, 12.011, because there's some carbon-13 and some carbon-14 that raise that up. It's about 1% carbon-13, if I remember correctly, and less carbon-14. And we previously discussed 2 fundamental forces of nature, gravitational and electromagnetic. The electromagnetic forces hold the between the proton and electron is 10 to the 39 times greater than the gravitational forces between those 2 particles. So the electromagnetic forces are the only important forces on electrons and are responsible for the structure of atoms, molecules, and all matter in general. Every everyday force other than gravity you encounter is electromagnetic. Pretty much. Now, the nucleus of any atom is really small, and it's packed with neutrons, which don't have any charge, and protons, which are positively charged. So the electromagnetic force is constantly trying to make the neutron explode, the nucleus explode itself. So the repulsive forces in the nucleus are huge, and the nucleus should fly apart. So there needs to be some additional force holding the nucleus together. This is the strong nuclear force, because sometimes names aren't very creative. There is a strong nuclear force and a weak nuclear force. And it's the thing about the strong nuclear force is that it's the strongest of the fundamental forces, but it only acts over very short distances. So it's attractive at distances less than about 10 to the minus 14 meters. And it causes all the things in the nucleus to attract each other. And it's actually what holds together the protons and the neutrons. Because it turns out they have component parts as well. So for a large nucleus, the forces become kind of complicated. Any individual proton is only attracted by the 6 or 7 closest nucleons, but it's repelled by all the other protons. So when the number of protons exceeds about 83, the electrical repulsion overcomes the nuclear force and the nucleus becomes unstable. So spontaneous disintegration or decay will occur to adjust for neutron-proton imbalance. Now, that may take a very long time, but it is something that happens. So basically, all big nuclei are unstable. And you'll see that to get closer to stable, you need a lot more neutrons than protons, which is why, the mass of large things like uranium is more than just twice the number of protons. It's, quite a bit more than that. So physicists have also identified a weak nuclear force within the atom. And this is also a very short-range force. The way it is short-ranged is different than the way that the strong nuclear force is short-ranged. And it reveals itself primarily in something called beta decay. It's weaker than the strong force and the electromagnetic force. And these these known atomic forces, the electromagnetic, weak nuclear, and strong nuclear, have all been organized into a unifying theory called the Standard Model. So we understand how they would merge at high energies and things like that. The weak nuclear force is what allows most common radioactivity to occur. So beta decay is a process by which protons can turn into neutrons and neutrons can turn into protons. So it's one of the important types of radioactivity. So that's one of the, and it involves the weak nuclear force. So again, mass number is the number of protons and neutrons, or the total number of nucleons. An isotope is the number when the number of neutrons vary in the nucleus of a given element. And the atomic number is the number of protons. Now, radioactivity is the spontaneous process of a nuclei undergoing a change by emitting particles or rays. So a nucleotide is a specific type of nucleus. It's a specific isotope, like uranium-238 or carbon-14. So it's not just a specific element, it's an element at a specific mass with a specific number of protons and neutrons. Radionucleotides, or radioactive isotopes or radioisotopes, are nucleotides whose nuclei will spontaneously decay to become some other nucleus and emit radioactivity. And substances that give off such radiation are said to be radioactive. So, for example, uranium-238 or carbon-14 are both radionucleotides. So uranium-238 is not very radioactive. It is a bit. I don't remember how it decays off the top of my head. Carbon-14 does decay, and it's used for carbon dating. So when you have radioactive decay, you have some parent nucleus, the original nucleus you had before the decay, and then the daughter nucleus or daughter product, which is the resulting nucleus after the decay. And there's three, I think uranium-238, if I remember correctly, squirts off an alpha particle. I could be wrong. There's three common ways. alpha decay, beta decay, and gamma decay. Alpha decay decreases the number of protons. There's two types of beta decay, but usually beta decay increases the number of protons and decreases. Alpha decay decreases the number of protons and neutrons. Beta decay doesn't change the total mass, but it changes a proton into a neutron or vice versa. And then gamma decay doesn't change any of the neutrons, but the nucleus is relaxing. In alpha decay, this is the disintegration of a nucleus into a nucleus of another element with the emission of an alpha particle, which spits out a helium nucleus, which is, 4 nucleons, 2 protons, and 2 neutrons. Beta decay is when a neutron is transformed into a proton with the emission of a beta particle. The opposite can also happen. So a beta particle is actually an electron. You can also have a proton turn into a neutron, and it will emit an anti-electron. And then lastly, gamma decay occurs when a nucleus emits a gamma ray and becomes a less energetic form of the same nucleus. So those are the 3 types of decay. Often gamma decay happens after one of the other types of decay because it decays into an energized state and then it relaxes by releasing a gamma particle. And in general, you can identify what particles you're dealing with. If you have something spitting out particles and you put them in an electric field, the alpha particle will be attracted towards the negative plate because it's positively charged. The gamma ray will go straight because it's not charged. And the beta particle will be attracted towards the positive plate because it's negatively charged. You can do a similar thing in a magnetic field. It'll bend the paths. So alpha decay, thorium-232 will decay to radium-228 plus an alpha particle. And notice how it goes from having 90 protons to 88, and from 232 total nucleons to only 228. So if you add up the top numbers, they add up. If you add up the bottom numbers, they add up. Beta decay, carbon-14 decays into nitrogen-14, where one of the neutrons turns into a proton and it spits out an electron. So the mass doesn't change because the electron basically has no mass, but you have 7 and a -1 from the electron. And you can have gamma decay. Lead-204 energized will relax to lead-204 plus a gamma ray. The sums of the mass numbers on top will always add up, and the sums of the atomic numbers will add up. And we give the electron a negative atomic number. So uranium-238 undergoes alpha decay. So this will decay from 238.92 to something and an alpha particle, which is a 4,2 helium-4. So that's going to be 234.90. That is thorium-234. Yeah, uranium-238 decays to thorium-234. And that's one of the more common ways that it decays. So an alpha particle is a helium nucleus. It is a charge of +2 and a mass number of 4. A beta particle is an electron. It has a charge of -1 and a mass number of 0. Gamma particle is light. A gamma ray is light. It's electromagnetic radiation. It has a charge of 0 and a mass number of 0. You can also have a positron. So you can have when a proton turns into a neutron, it emits a positron, which is an anti-electron. It has a charge of +1 and a mass number of 0. And sometimes also nuclei will spit out neutrons. And a neutron has a mass of 1 and atomic number of 0, a charge of 0, and a mass number of 1. So here, for example, is the decay series for uranium-238 to lead-206. So uranium-238 decays to thorium-234, which beta decays to, I can never remember what this is called. Pa-234, which then beta decays to uranium-234, which alpha decays to thorium-230, which alpha decays to radium-226, which alpha decays to I don't remember what Rn is off the top of my head. 222, which goes to polonium-218, which goes to lead-214, which beta decays to bismuth-214 to polonium-214, to lead-210, to bismuth-210, to polonium-210, down finally to lead-206. Oh, this is ruthenium, I think. I could be wrong. So which nucleotides are unstable, radioactive, and which are stable? Most stable nucleotides have an even number of both protons and neutrons, even. Most unstable nucleotides have an odd number of both protons and neutrons, odd. So a nucleotide will be radioactive if its atomic number Z is greater than 83. If the number of neutrons is less than the number of protons, with 2 exceptions, just hydrogen 1 and helium 3. Only for the lightest of elements are there exceptions there. Or if it's an odd nucleotide, with a few exceptions as well. Deuterium is stable. Lithium-6 is stable. Boron-10 is stable, and nitrogen-14 is stable. Again, the very smallest ones. So here, we're going to identify the radionuclide in each pair. That's not helium. 222 or 86, that shouldn't be helium. 86 is oh, Rn is great. That should be radon, not helium. I don't know why that says helium. That's typo. Let me see if I can fix that. No, that's a picture. Well, I must just be wrong. That's radon. It should be Rn, not helium, because it's an 86. This is unstable because of a Z above 83. It's also just wrong. Neon 1910 has fewer neutrons than protons, so it's going to be unstable as opposed to neon 20. And copper 6329 versus copper 6429. This is odd. This has an odd number of both protons and neutrons. Turns out odd numbers of protons and neutrons are just less stable. Has to do with how they interact. So even tends to be stable. Even odd is sometimes stable, and odd even are also often have decent number of stable nuclides, but odd only has a few, 4. Even has 160. And there's basically a band of stability. This is all the known nuclides. The red dots are the stable ones. So you can see this sort of middle band is the stable nuclei. And all the little blue dots are radioisotopes. So when we talk about radionuclides, they may be unstable, but it may take a very long time for them to decay. And the way we talk about how fast they decay is with the half-life. So half-life is the time it takes for half the nuclei in a given sample to decay. So after one half-life is expired, only half the original number of radionuclides remain undecayed. After two half-lives, only a quarter remains. After three, only an eighth. So it's an exponential decay. This is the decay curve for any radionucleotide. This is the starting value. This is the number of half-lives. After one, you're at half the original. Two, you're at a quarter. Three, you're at an eighth. After four, it'd be at a 16th. So what fraction in mass of a 40 milligram sample of iodine-131 with an half-life of 8 days will remain in 24 days? Well, 24 days is 3 half-lives. So we start with the given amount, 40 milligrams, and we have it 3 times. So we divide by 8. And so 40 milligrams divided by 8 will leave 5 milligrams of iodine-131. Now, if instead what fraction of strontium-90 produced in 1963 with a half-life of 29 years will remain in 2021? So that's 58 years. That'll be 2 half-lives. So it will be a quarter of the starting value. So a fourth of the starting amount of strontium-90 remains. Things with shorter half-lives well, because they decay faster, they pump out more radioactivity usually. And then how long would it take a sample of carbon-14 to decay to 1/4 its original activity? The half-life of carbon-14 is 5,730 years. So the carbon-14 would need to decay for 2 half-lives in order to be reduced to a quarter of its original activity. And that is 11,460 years. If you've heard of carbon dating is using the amount of carbon-14 in formerly living things to figure out how old they are. And that works because the carbon-14 in your body, even though it radioactively decays, is constantly replenished. Because new carbon-14 is constantly created in the upper atmosphere. And so as you breathe or interact with the atmosphere, the amount of carbon-14 in your body is constantly replenished, but that process stops as soon as you die. So once you die, that carbon-14 will just steadily decay, and you can use that to figure out how old things are. And that's carbon. So in order to determine the half-life of a particular radionucleotide, you need to monitor the activity of a known amount in the laboratory. So you look at how much decays over a certain amount of time, and then you can work out, when the activity has fallen to 1/2, you've reached 1 half-life. If that half-life is very long, you can work out what a half-life would be from a relatively short time by figuring out how much it decays in that time. This is usually measured with some sort of detector, like a Geiger counter. A Geiger counter, when you have a high energy particle from a radioactive source, enters a window on the Geiger counter. It energizes, it will ionize an argon atom, which will create an electric current, which will create a click that you hear, which gets counted and amplified into the familiar clicks. There are other things that you can use to detect other than argon. I believe these days they mostly use solid state scintillator materials, but that's a traditional Geiger counter. What a traditional Geiger. And because of their constant decay rate, you can use radioisotopes as clocks. You can use them to measure the age of objects that contain radioisotopes. And this is used to both date formerly living things with carbon dating, but also to date rocks and stuff. Because when they formed, they trapped, only certain elements are included, and then those elements will decay to elements that act differently chemically, and will basically go away. So that's a useful thing. So carbon-14 dating is an important dating procedure in archaeology. It's used on materials that were once parts of living things like wood, bones, parchment, etc. Because carbon-14 is formed naturally in the upper atmosphere and dispersed by atmospheric mixing. all living material that interacts with the atmosphere contains about the same level of carbon-14. We're an activity level of about 16 counts per minute per gram of total carbon. It's a little more complicated than that because that amount has changed a little over time, and there's whole things, but you can calibrate for it. And once an organism dies, it ceases to take in carbon-14, and the carbon-14 present at death starts to undergo radioactive decay. And therefore, the longer the organism has been dead, the lower its radioactivity of each gram of carbon, because the carbon-12 and carbon-13 are stable in its remains. And we've gotten better and better at carbon-13 dating, so we can get more and more accurate measurements from tinier and tinier samples. But this is sort of the process. Cosmic rays react with nitrogen-14 atoms to make carbon-14. The carbon-14 reacts with oxygen to form carbon dioxide. That carbon dioxide is acquired by plants and eaten by people and becomes part of the body, and then you die and you stop exchanging carbon-14 with the atmosphere. After about 10 half-lives, very little carbon-14 remains, and therefore it's barely measurable. And the limit of radiocarbon dating depends on the ability to measure very low activity in old samples. The current limit is, I think, a little better than 40,000 to 50,000 years, but somewhere around there. The real thing is we've been able to use smaller and smaller samples for carbon-14 dating. I don't know what the actual limit. I think they can make it to about 100,000 years now, but I'm not 100% sure there. But yeah, 40 to 50,000 years is about the actual limit. I don't know what the current limit is. It's a bit better than when this slides were written. So if you find an old scroll in a cave that has a carbon-14 activity of 4 counts per minute per gram of total carbon, approximately how old is the scroll? The plant from which the scroll was made originally had an activity level of 16 counts per minute. You get to 4 counts per minute. That's 2 half-lives. Carbon-14 has a half-life of 5,730 years. So the scroll is between 11,000 and 12,000 years old. That, however, doesn't really make sense because that is older than scrolls existed. But yeah. We know that radioactive nuclei can spontaneously change into one nuclei of other elements, which is a process called transmutation. And scientists wondered if the reverse was possible. Could a particle be added to a nucleus to change it to another element? And the answer is yes. And this process is called a nuclear reaction. So yes, it is possible to turn lead into gold. It has actually been done. It is entirely not cost effective at all. It costs enormously more than the gold is. You're talking millions of dollars to make fraction, tiny fraction, dozens of atoms of gold or something like that. It's ridiculously expensive. So in 1919, Ernest Rutherford produced the first nuclear reaction by bombarding nitrogen-14 with alpha particles. And the result was an artificial transmutation of a nitrogen isotope into an oxygen isotope. You went from nitrogen-14 in the helium nucleus to oxygen-17 and a proton, a hydrogen nucleus. And you'll note that the mass number and the atomic number are conserved in nuclear reactions, just like in nuclear decay. So the total mass on each side is 18. The total atomic number on each side is 9. And the general form for a nuclear reaction is A plus A equals B plus B. So you get, nuclei A is bombarded with particle little a to create nuclei B, which emits particle B. And so these are common particles that occur, but you also sometimes get deuterions, protons. Oh, these are all off by 1. oops, protons, deuterions, and tritions are often encountered in nuclear reaction. Let me see if I can fix that. Or if this is. Okay, yeah, this is messed up, but I don't really care. Okay, this is a mess. Maybe I'll fix it in a few. So for example, if you bombard lithium-7 with a proton, so hydrogen plus lithium, you get the sum of the mass on the left has to be 8. You get a neutron out. Sum of the mass on the right has to be 8. You're gonna get beryllium-7 plus a neutron. And if you bombard aluminum with deuterium, you get magnesium 25 plus an alpha particle. And if you actually want to transform it to bigger things, you tend to bombard with calcium 20, I think. It just happens to have nice properties for this. Now, Rutherford's discovery of the transmutation of nitrogen 14 into oxygen 17 was actually an accident, but the implications were enormous. One element could be changed into another completely different element. And it's not possible to actually make gold from other more common elements. So if you bombard mercury 200 with hydrogen, you get gold 197 and a helium nucleus. The actual process, they started with beryllium and went up to gold. It's more than $1 million per ounce. It's quite a bit more than $1 million per ounce. So it's definitely not cost effective. Now, neutrons produced in nuclear reactions can be used to induce other nuclear reactions, so you can get a chain reaction. And since neutrons don't have an electrical charge, they're particularly efficient in penetrating the nucleus and inducing a reaction. And without an electrical charge, neutrons aren't influenced by positive or negative atomic charges. Now, what that means is that for certain elements, they're not so stable if you hit them with a neutron. And they'll fall apart violently. So the transuranium elements are those with atomic number greater than 92. All of these elements are synthetic. They're generally created in the lab by bombarding a lighter nucleus with alpha particles or neutrons. Or the most heavy elements these days are bombarding these elements with actually other elements. Like I think calcium 20 is getting popular. I think it's calcium. Or no, calcium is 20, calcium 40, or something like that. I don't remember the time. There's only so much jump you can make. It's not calcium 20, it's calcium 40. But so if you bombard uranium-238 with a neutron, it turns into Neptunium-239 and spits out an electron. If you slam iron into bismuth, iron-58 into bismuth-209, you get, I don't remember what this is, Nt-266 and a neutron. Now, you could also slam small nuclei together and merge them. So hydrogen, helium, and lithium are thought to be formed in the Big Bang. And beryllium up to iron were likely made in the cores of stars by fusion. And any atoms heavier than iron are thought to have formed during supernova explosions of stars when there was an abundance of neutrons and medium-sized atoms flying about. Our best understanding of this is actually a bit more complicated than that, but I'm not going to go into that because this isn't an astronomy class. Now, radionucleotides are actually quite useful. We use them all the time. They have many uses in medicine, chemistry, biology, geology, agriculture, and industry. So medical uses involve, you can use them, since they emit radiation, if you inject them into your body, they basically make the areas that they enter glow, emit radiation. So you can track how they move through your body. So one medical use involves a radioactive isotope of iodine, iodine-123. It's used in a diagnostic measurement of the thyroid gland because you're studying the amount of iodine your thyroid gland pulls in, because your thyroid gland uses iodine. And americesium-241, which is a synthetic transuranium radionucleotide, is used in many common household smoke detectors. It emits radioactivity, which is detected. When smoke enters the smoke detector, it blocks that radioactivity. There's a reduction in the detection signal, sets off the smoke detector. There are other ways to make smoke detectors. I don't know if they're that common these days, but it's a pretty common type of smoke detector. So a weak radioactive source ionizes up the air and sets up a small current. If smoke particles enter, the current gets reduced, causing an alarm because it absorbs some of the radiation. And in both chemistry and biology, radioactive tracers like carbon-14 and hydrogen-3 are used to tag an atom within a molecule. So in this way, the reaction pathways of drugs and hormones can be determined. In geology, the predictable decay rate of radioactive elements in rocks and minerals allows us to date rocks and minerals. And in industry, tracer radionucleotides help manufacturers test their durability. And a lot of these are very mildly radioactive. So they aren't like a huge deal to be around. They often don't last very long. Or, they're very mildly radioactive where they don't last very long. Some are used as radioactive sources for other things like cesium-138 or whatever it is. You may have heard about the radioactive shrimp story recently. That was a medical source got damaged and leaked radioactive cesium on the shipping container, in the shipping container that shrimp was in. It ended up in the wrong place in a recycling plant, so a bunch of that got let out. That's used for medical devices as a source of, actually, to make X-rays. Now, when you have a really big nucleus, one of the ways it can literally split in half. This is nuclear fission. So that's when a large nucleus splits into two intermediate-sized nucleus with the emission of neutrons and a conversion of some of that mass into energy. So, for example, uranium-236, which you can get by hitting uranium-235 with a neutron, fissions into two smaller nuclei, will emit several neutrons and release energy. So, if you have uranium-235, and you have enough of it, sometimes it will emit neutrons. And then when it fissions, uranium-236 fissions, it spits out neutrons, which can make more uranium-236, which will fission, and so on. So here's an example. We have uranium-236 going to krypton-88 and barium-144, I think. So 4 additional units of mass are needed on the right. It ends up being 4 neutrons because the atomic number is 0 and the mass number of 4. So this ends up being 4 neutrons. Here, uranium-236 becomes strontium-90 and xenon-144, and 2 neutrons. But you can see all these uranium decays spit out a few neutrons, which then cause more uraniums to split. Now, the products of fission are always radioactive. Some of these have half-lives of thousands of years, which can lead to issues with the disposal of nuclear waste. But relatively large amounts of energy are produced, and neutrons are released. So nuclear fission is very useful to create big amounts of energy. Nuclear waste isn't that hard of a thing to deal with. Yes, they have thousands of years of half-life, but it's not that hard to contain because the amount of fuel used is so small, it's a very small amount of material. So you get a chain reaction. In an expanding chain reaction, one initial reaction triggers a growing number of subsequent reactions. In the case of uranium-236, each fission emits 2 neutrons. Each of these 2 neutrons can hit another uranium-235, resulting in the fission of 2 additional 235 nuclei and the release of energy, and 4 neutrons, and so on. And as the chain expands, the number of neutrons emitted and the energy output increases. So if you have a ball of so uranium-235 will absorb a neutron, initially changes into 236, and then immediately undergoes fission, releasing 2 neutrons and energy. And those neutrons can cause more uranium-235 to fission. So if you can control how much these neutrons can hit other uranium-235, you can control this process. That's what happens in a nuclear reactor. And if you can ensure that they're almost always going to hit 235, another uranium-235, you can make this happen very fast and very violently. That's what happens in a nuclear bomb. So if all the emitted neutrons hit another uranium-235 nucleus, this results in an increasing number of emitted neutrons, fission reactions, and energy release. You get an expanding chain reaction. That is what you're trying to cause in a nuclear weapon. But you can also have a self-sustaining chain reaction, where only half the neutrons hit other 235s. And you get a steady release of energy can be obtained, where each fission event causes only one more fission event. For a self-sustaining chain reaction to proceed, the correct amount and concentration of fissionable material, uranium-235, needs to be present. If there's too much fissionable material, you get an expanding chain reaction. If there's too little fissionable material, the chain reaction will stop. In a nuclear power plant, things are generally set up so that you are below where you'd have a self-sustaining chain reaction. But if you add something to help the neutrons hit other uranium-235s, what's called a mediator, you can either add something that prevents, that's what a control rod does, or you can add something that helps cause these things to hit more 235. That's called a mediator. And control the rate of fission. And that's what happens in a nuclear power plant. So the critical mass is the minimum amount of fissionable material necessary to sustain a chain reaction. It's about 4 kilograms of pure uranium-235. A subcritical mass, no chain reaction occurs. A supercritical mass, an expanding chain reaction occurs. A nuclear weapon is designed to take, well, the simplest ones take 2 subcritical masses and combine them to form a supercritical mass. So natural uranium contains about 99.3% 238 and only 0.07% fissionable 235. Therefore, the 235 needs to be concentrated or enriched in order to create either a self-sustaining or expanding chain reaction. In U.S. nuclear reactors, the uranium-235 has been enriched to about 3%, enough for a self-sustaining chain reaction, but not enough for a weapon. Nuclear weapons require enrichment of about 90% or more 238 for a sudden release of energy. And to create a fission bomb or an atomic bomb, a supercritical mass of fissionable material must be formed and held together. So The simplest way is that subcritical portions of the fissionable material are held apart until detonation, and then a conventional explosive brings these segments together to create a supercritical mass capable of an explosive release of energy. And this sudden energy release is due to an expanding chain reaction of the fissionable material. There's a couple ways to do this. The simplest way is you have like two halves of a sphere and you slam them together. But a lot of the more advanced things use what's called an implosion thing, where if you compress a mass that is subcritical, it will become supercritical and go kaboom. So actually the first nuclear bomb was an implosion because that was the harder one to pull off. So the Trinity test was an implosion. And then of the ones dropped on Japan, one was gun type and the other was implosion, I think. Now nuclear reactors are designed to never go supercritical and go crazy. They have to have a controlled and continual release of fission energy. And the first intentional fission chain reaction was in a nuclear reactor. It was a controlled one. And it was actually in Chicago, on the University of Chicago campus, in a squash court. So nuclear reactors have to have a controlled and continual release of fission energy. So within the reactor core, you have long fuel rods and control rods. The fuel rods contain the fissionable material. This is the heat source. The control rods contain a neutron absorbing material, such as barium or cadmium. These control the rate of nuclear fission and the amount of heat really produced. So if you insert the control rods all the way, they're absorbing the neutrons, preventing more fission from occurring. There are also what are called mediators. These slow the neutrons down to a speed that makes them more likely to interact with uranium and basically speed up the process. So we have slow down things, which are the control rods, and you have speed up things, which are mediators. And this is sort of what they look like. The tubes for the control rods and tubes for the fuel rods. And the pellets are uranium oxide pellets that have been concentrated to have more uranium-235. And since the fission rate in the fuel rods cannot be directly controlled, the control rods are inserted or withdrawn between the fuel rods to control the number of neutrons being absorbed. And the reactor core basically boils water. It's a heat source. The heat is continually moved by a coolant, which is water flowing through the core. And then this is used to generate steam in a steam generator. Generally, you have hot, very, very hot, high pressure water in the reactor, which is used to heat up lower pressure water, which turns into steam that runs the steam generator. So things are separated. So the water that's in contact with the actual nuclear fuel never actually leaves and becomes steam. So this is how it works. You have control rods, you have hot water circuit, which is at high pressure. So it never actually becomes steam. And then you have a lower pressure circuit that boils the water to steam and drives the steam turbine. And then that is cooled with outside things. So the hot water circuit is completely contained, so there's no radioactive contamination. Nuclear power plants are ridiculously safe. Like the number of people who've been killed in nuclear accidents is like less than 20 ever. And most of those weren't at nuclear power plants. Yeah. So the reactor coolant, H2O, performs two critical functions. Coolant transfers the heat from the reactor core to the steam generator. It also serves as a moderator. Water is a moderator. So the neutrons that are initially emitted from the fuel rods are moving too fast to cause uranium-235 to fission efficiently. But if they run into water, they slow down a bit and they work better. Now, nuclear reactors do have potential dangers. The amount of heat generated needs to be controlled. The fission rate is controlled through the insertion, slow down or withdrawal speed up of the control rods. And the heat generated must be continually removed from the core, or else things can explode, and that's bad. An improper control or removal of core generated heat can result in the fusing or meltdown of the fuel rods. And when your fuel melts, you get horrible radioactive, And the uncontrolled fissioning mass will become extremely hot and will literally melt through the floor of the containment structure. And it generally also causes a steam explosion, scattering radioactive material around. The extremely hot and uncontrollable radioactive material will enter the outside environment, the groundwater and atmosphere. Not good. There's 3 well-known nuclear accidents that have ever occurred. 3 Mile Island, an accidental shutdown of coolant led to a partial meltdown. This resulted in very little escape of radioactive gases. Basically, nobody was affected. And we learned that about interface design, because 3 Mile Island, that accident was caused by the fact that, like, there were too many warnings and they were really confusing, and it was basically the controls were really hard to understand. Chernobyl, a complete meltdown occurred due to poor human judgment and design problems, and like turning off safety systems. There's just the string of stupid involved in Chernobyl is kind of terrifying. And this resulted in an explosion and fire in their new reactor core and significant regional contamination. And then at Fukushima, a severe earthquake caused power loss, and tsunami waves disabled backup generators. And this resulted in a partial exposure of 3 reactor cores, causing a hydrogen gas buildup, which exploded, releasing some radioactive material. But really, nuclear reactors are not that bad. And then there are things like breeder reactors, which we use to make heavier elements. So besides the uranium-235, another fissionable nucleotide is plutonium-239. And plutonium-239 is produced by the bombardment of uranium-238 with fast neutrons during the normal operation of a nuclear reactor. So in a breeder reactor, the production of plutonium-239 is promoted. And then this is separated and can be used in an ordinary nuclear reactor or in nuclear weapons. So plutonium-239 is a natural byproduct of a nuclear reactor. 20 breeder reactors running for a full year produce enough plutonium-239 to run another reactor for a full year. And breeder reactors run at a higher temperature than conventional reactors and use liquid sodium as a coolant. And there's a bunch of new nuclear reactor designs, including ones that use like liquid salt as a coolant and things. People are trying to do. Pebble beds there's now actually a pebble bed reactor out there. China developed a functional pebble bed reactor just a couple years ago or something. So this is the possible next generation for nuclear reactors. They use graphite uranium pebbles instead of fuel rods. And the reactor is cooled by non-explosive helium gas instead of water. The helium is inert and doesn't become radioactive. Graphite is a good moderator, slowing down the phasing neutrons. And the thing about a pebble bed reactor is that they're basically designed to fail safe. If something goes wrong, the failure state is not fissional. They turn themselves off when something breaks. So they don't melt down. So they're a lot safer. So they dissipate heat on their own, and they can be shut down by removing pellets and just sort of spreading them out. Now, nuclear fusion is the process by which smaller nuclei combine to form a larger nuclei, along with the release of energy. It doesn't require a critical mass. It's the source of energy for the sun and other stars. In the sun, we use this wonderful thing where 4 hydrogens turn into a helium, some other stuff, and energy. Some positrons and some gamma rays and some neutrinos and energy. And that's happening all the time. We can't do that easily on Earth. because the speeds were, the problem is that these are positively charged. You need to slam them together really fast to make them combine. The sun cheats by being super dense and super hot. For us, we want to do something more like this. Two hydrogen deuteriums combining to form helium-3 and a hydrogen. This is a deuterium-deuterium reaction. I believe this is the one that's most likely going to be used for actual break-even nuclear reactor, fusion reactors. So far, no fusion reactors produce more energy than they put in, because it's just hard to do it efficiently at the pressures and temperatures we can reach on Earth. The sun cheats by being super dense and super high pressure and super hot. Well, we actually get hotter than the sun because we can't get super high dense and super high pressure. Deuterium and tritium form an alpha particle and a neutron. That's a DT deuterium tritium reaction. This is what we use in hydrogen bombs. Those are efficient, but you also start them with regular atomic bombs. You need an enormous amount of energy to kick them off. So that's a DT fusion. So technical hurdles of nuclear fusion. The repulsive fusion force between two positively charged nuclei is very great. To overcome these strong repulsive forces in a nuclear fusion, the particles have to be heated to extreme temperatures. And at these extreme temperatures, things get complicated. And so far, containment of the material uses up too much energy. So it's a plasma. To hold the plasma in case is tricky. The plasma has to be confined at a high enough density. And with today's technology, it's a significant challenge to reduce the necessary temperature and confinement requirements. There's one claimed break even, but there's no actual real break even. So there's something called inertial confinement, where basically you slam it with all directions with really powerful lasers. And that's the experiment that claimed to get a break even, but they sort of cheated. They ignored some of their inefficiencies. Simultaneous high energy laser pulses from all sides cause a fuel pellet of deuterium and tritium to implode. And this causes fusion. And this is conducted at Los Alamos and Lawrence Livermore labs. And it's really done because this is how we can sort of simulate nuclear bombs without actually testing nuclear weapons. Real nuclear fusion is done with magnetic confinement. We may get a reactor at some time, but use donut-shaped magnetic fields to hold the plasma, while electric currents raise the temperature of the plasma. And magnetic and electric fields are useful since plasma is a gas of charged particles. And the leading experimental stuff is actually all in Europe at this point. They're building the best one. It has a low cost and abundance of deuterium. Deuterium is easy and cheap to get. You can just get it out of water. Nuclear waste isn't a problem, it's just hydrogen. Relatively few radioactive byproducts, they have short half-lives. And fusion reactors can't get out of control. Things just quickly cool down. Yeah, but yeah, we'll stop there. It's not going to be in the test anyways. Have a nice day. I'll see you next week.